Hello everyone, this is a supplementary tutorial for AA228 CS238, Stanford University, Fall 2018. I'm Shushman Chaudhary, one of your TAs, and in this video I'll be giving you some details about how to compute the Bayesian score, which is something that you'll need to do for your programming project 1. I should stress that this is a supplementary tutorial only, so it does assume that you've been following along either by watching the lectures and also by reading the book, Decision Making Under Uncertainty by the course instructor Michael Kokendorfer. But I'll try to provide details throughout the video that should help you do the project 1. There'll be three main things that I'll cover in this video, so you should feel free to fast forward. If only some things are of relevance to you, I'll post the breakdown of times for these three parts in the video description as well, so you can check the link underneath for that. Firstly, I'll just provide some details of computing the Bayesian score given a graph G and a dataset D. I'll start mostly from scratch, but I will assume that you are at least looking at the book and the notations in it. Secondly, I'll provide some hints for how you do this with your code, which is what you have to do for programming project number 1. And finally, I'll talk a little bit about how you can efficiently recompute the score given some small changes to your graph, which is also something that you need to do. I'll emphasize that computing the Bayesian score is only one part of the project. The rest of it is actually figuring out a good structure for the graph, and that will use your Bayesian score. So we don't want you to get hung up too much on the computation of the Bayesian score, which is one reason why we're releasing this supplementary tutorial. And that lets you focus on the structure learning aspect, which is really primarily what the assignment is about. So with that said, I'll just get started. So the setting that we have, and to follow along, you should look at page 46 of the DMU book. For those of you who don't know what the DMU book means, I've put the description in the YouTube comment section below, in the video description below, sorry. So there are n discrete variables indexed x1 through xn. Given some Bayes net g over those variables, we have the following definitions. For the ith variable xi, there are ri possible instantiations of xi. So there are ri possible values that xi can take. And there are qi possible parental instantiations of xi. So whatever the number of parents that qi has, the number of parents that xi has, there are qi possible combinations of values that its parents can take. And one thing to note is that qi is 1 if xi has no parents. One bit of notation is that pi ij at the bottom here is denoted to be the jth instantiation of the parents of xi. So that defines pi ij. These are just indexing choices. I'll give some examples of what these indexing choices refer to in a little bit, but they are used to have a consistent notation in the book. Don't let that be too confusing. The second thing that we need in our setting is some dataset D, a dataset of samples generated from the Bayesian network. And given this dataset D, the other bit of notation that we'll need is this right here, mij, which is the number of times in the dataset the variable xi takes on its kth value when its parents take on their jth value. So mij is defined by I, j, and k. And again, I'll work through an example of this in a little bit. That should make that even clearer if it isn't already. But this is what mij refers to. Given the setting rather, the first part of the homework is computing the Bayesian score. And that, let me just zoom out a little bit. So that's equation 2.83, which is what I'm going to show you right now. That's on page 47 of the book. Again, there's a little bit of notation, but as you'll see, it's really just a subset that we need to focus on. But this is the full equation, ln p of g given d, where g is the Bayesian network structure, given the data set of samples that you've been given, D, which in the case of the project you are given. We're computing the logarithm of that because this will usually, the value itself will be really small, so we take a logarithm to avoid underflow. And that just expands to be the prior probability of the graph itself. Let me actually write that here. So that's the prior, and this is essentially the likelihood of the data given the graph structure. So that's, yeah, so that's the likelihood. And again, the book has sort of an elaborate derivation for what this function is, for this formula is, and this is just the gamma function, and you can look that up. And the alpha ij zeros and the mij zeros here are just summing up over summing the alpha ijks and the mijks, summing over the values of xi each time. And of course, the alpha ijks refer to the pseudo counts. So these are pseudo counts, and will all be 1 for the homework. And these are the actual counts that we defined above. Oops. Just want to go back here and say, so this is what the definition of mij. So given a graph G and given some data set D, you essentially need to implement this equation. Bear in mind that since we're assuming that there's a uniform prior over graphs, we can just disregard this. Okay, I used the rainbow pen there, but anyway, we can just disregard that. We can just focus on the term on the right-hand side here. And in fact, since we've already told you that all the alpha ijks are 1, and the alpha ij0 is just derived from the alpha ijks, really what it all boils down to, computing this score, it really just boils down to computing the mij values. So you're computing those counts for the graph given the data set. Does that make sense? So that's what we're going to do. And here's an example of what I mean. So for the general setting of x1 to xn, we have this data set of a bunch of samples. And I'll just mention that here. One row in this data set, we'll just call that a sample from the Bayesian. And there'll be many such samples going down like this. That's the data set that's given to us. And we are assuming that there is some G, some Bayesian structure, that we're assuming. And then of course the point of the project is to try out a variety of different Bayesian structures and compute the score for each of them. This is the general idea of computing the MIGKs. So what we want to do is, we want to consider a sample. So we're going to loop through the samples. So for each sample, actually let me put that inside, nest it here, because we're doing this for each sample. We want to loop through the xi's, which basically the variables. So I will go from 1 to n. And then for each of the xi's, so I'll nest that again. Let me move a little bit here. Look up the parent values in the sample. That'll give us our j, and the value of xi in the sample, that'll give us our k. And then increment the count mijk. That's the general idea. So for every sample, we go through the variables one by one. The sample gives us the values of the parents of each variable xi. or it has no parents, in which case we don't have to do this. We consider, and every variable xi has some value for that sample. We figure out the index of that, and then we increment the count. And I want to remind you, or rather, sorry about that. Let me just go on 1 sec. Yeah, I just want to remind you what mijk means again. Oops. All right. Now let's do an example. I think that will make it a little more clear. Oh, this is going crazy. So let's say we have three variables, A, which is binary, B, which is binary, and C, which is ternary. So it has three values. And let's say the values that they can take are 0, 1, 0, 1, 0, 1, 2. And let's say this is the graph structure that's given to us. So C and A and B are its two parents. And let's say this is our dataset example. You don't have to memorize this or anything. You might want to write this down for your own convenience. But this is the dataset that we're working with. It's of course really small, but hopefully working through those should give you an idea of what to do in general. Before we get into computing the Bayesian score, just to drive home the point of the indexing clear, let's actually do some indexing. So for this example here, and again, you might want to copy this down. Let's do some indexing just so that you get the idea clear. Oops, let me create some space over there. Some more space. All right. So for the various values of I can take three values, right? So when I is 1, let's let this column be the variable xi. And in our case, let's just let that be A. So I equals 1 corresponds to the corresponds to x1, which corresponds to the variable A for this particular case. If you recall, A has no parents here. So the next column, which is for parental instantiations, is qi. And as we defined earlier, over here, qi equals 1 if xi has no parents. So this is just 1. And then the number of values rather that it can take, which is ri. A is binary, so ri here is 2. But I'm going to actually, that's the number of values it can take. I'm going to expand that a little bit and just say that A can take 0 and 1 as its values. And therefore, ri equals 2. And k equals 1, k equals 2. So I'm just trying to link the actual values and the indices here in this example. And I think that will really help you make the connection between the indices and the values themselves. And actually, for the sake of completeness, j here should be 1. So you'll see in the book, you'll see the following notation. You'll see I going from 1 to n. You'll see nested within that, you'll see j going from 1 to qi. And you'll see nested within that, you'll see k going from 1 to ri. Well, I guess this isn't really nested because, yeah. So phi equals 1 to n. So for a particular variable, j is from 1 to I, which is the parents. And then k goes from 1 to ri, which is the values of the variable itself. And these are the variables. So this is some notation you'll see in the book, and this example is just to relate it to that. So that's when the case of I equals 1. Quite similarly, for the case when I equals 2, we have the variable being b. It doesn't have any parents, so its parental instantiations is 1. Again, for the sake of completeness, j equals 1. Actually, let me draw a line here. And then again, 0, 1. But again, these could have been some other values, whatever. It's defined to us through the problem. You have k equals 1, k equals 2. Let me expand this down a little bit. So that's this row. And then finally, for I equals 3, the variable xi is c. Now, the parental instantiations of C. So C has two parents, A and B, and each have two values. So the parental instantiations are the possible values that the parents of C can take. And those are the values of A and B. So that's 0, 0, 0, 1, 1, 0, 1, 1. And therefore, Qi equals 4. And actually, just for completeness, let me write that here as well. Qi equals 1. Oh, well, actually, I guess there are no parental values, so I didn't really need to write that. Qi is equal 1 because there are no values that parents can take. So Qi equals 4 for C. And just to keep up the indexing, j equals 1, j equals 2, j equals 3, j equals 4. Because recall, j goes from 1 to Qi. And so this is the indexing. This doesn't have to be the order. It could have been some other order. This is just the order that I'm choosing, and that's an order that you choose. And finally, 0, 1, 2, and therefore Ri is 3. Let me write this here for completeness, equals 2. And then k equals 1, k equals 2, k equals 3. So, so hopefully this sort of connects the indices I, j, k to the actual values of the variable. The point I want to make here is the following. Let me create some more space here. Oh, still not perfectly used to this guy. The point I want to make here is the following, is that I, j, and k, oh, I guess I made that here, never mind. Is that I, j, and k are indexing choices, and there's no connection to the actual values of the variables. The variables themselves could have taken strings, could have taken, alphanumerics, could have taken whatever. I, j, k are just the indexing choices, and so I could have used a different ordering here for k equals 1, 2, 3. The values themselves are defined by the problem structure, the values of the and the sort of the problem setting and the parental the structure of the Bayes net that defines the actual values that Qi and Ri have. But the indexing, the fact that for I equals 1, that it's variable A, that's a choice we made. The fact that for I equals 1, for j equals 1, because there's no other parental instantiation, the fact that k equals 1 corresponds to a equals 0 is a choice that we made. And so that's something to keep in mind, that that's an indexing choice that we've made. So anyway, based on the above, let's just do a couple of quick examples of what MIJK is actually referred to for this example. So again, I hope you've copied down the example. I'm not going to go back to it too often. I just want to make a couple of quick examples of MIJK. So for example, let's say 3, 2, 2. What does that mean? Let's write this out. This is I, this is J, this is K. I hope you copied down this table here, but for I equals 3, that's for C. So this is equal to, C is the variable we're considering, so count of C equals, now I equals 3 means C is the variable we're considering, but which value of C are we counting for? That's K. So K being 2. And from this table, K being 2 refers to C being 1. So this is the count of C being 1. But there's more to it because it also depends on the parental instantiation. The value of J is 2. And according to J equals 2, the AB is 0, 0, 1. So this is the count of C equals 1, A equals 0, B equals 1. So the point is, every time you see this in the data set, you'll want to increment the count M322, if that makes sense. Now that's not to say that, one point to make here is that one sample increments multiple MIJK values. So it's not that every sample corresponds to a single MIJK being incremented. In fact, each sample increments n n mij counts, right? One for each xi. So every sample involves the incrementing of n different mij parameters. Which mij you increment depends on which variable you're considering. And so that's the way to look at it. And again, we'll go through an example of that shortly. But let's just do one more example here, M211. So again, let me just switch that here. This is I, this is J, this is K. I'm just going to write it out here, and hopefully you would have figured this out. So you can pause the video and just make sure that you can do this correctly. But what this ends up being is just the count of B equals 1. Because when I is 2, that corresponds to B. B is the thing we're considering. J has to be 1 because B can't take anything else in that index. And then for K equals 2, oh, I'm sorry, it's a mistake, my bad, equals 0. So for K equals 1, it's the value of B equals 0. And then that's the count of B equals 0 in the data set. All right, and so the point to make here is this is regardless of C and A. Whatever their values are, if you see B equals 0, you'll increment the count of M211. And so you can see there that immediately any sample that is B equals 0, you'll increment the count of M211, but you'll also be incrementing other M counts. So every sample involves incrementing multiple counts. Let's quickly go through the data set here. So I'm hoping you copied this down, and I'll just go through one by one and do some quick examples. So if ABC is 1, 1, 1, based on that general procedure that I showed earlier up here, let me just go back to it. We're going to consider a sample. We're going to loop through the variables, look up the parental values and the value itself, look up the indices, increment the count. So for ABC equals 1, 1, 1, just demarcate this here. So for I equals 1, the variable we're considering is A, which happens to be 1, by the way, in that sample. And A obviously doesn't have any parents, and A equals 1 corresponds to K equals 2. So the count will increment here is M1 for I equals 1, 1 for J equals 1 because A doesn't have any more parents, and 2. That's the count will increment. Similarly, for I equals 2, we're considering B, which has the value 1. So M, this is going to be 2 because that's the I we're considering. B has only one parent, so that's 1. And then again, for B equals 1, the K index is 2. So 2, 1, 2 plus plus. And then 3, C equals 1. I equals 3, so that's the first one. Now, C has parents, so to figure out the J index, we need to look at the value of AB is 1, 1. Go back up to our table. For AB 1, 1, we have J equals 4. So that's 4. And then for C equals 1, the value of K is 2 here. So 3, 4, 2 plus plus. I'll work through one more example, but that should make the rest of the things clear. The second thing in the data set was, I'll just go up here, but hopefully 0, 1, 2. Again, for I equals 1, we're considering A, whose value is 0. A doesn't have any other parents, so nothing else really matters. So I equals 1, J equals 1, K equals 1 this time because we're considering the value A equals 0. For I equals 2, we're considering B, its value is 1. Again, B doesn't have any other parents, so this will be 2, 1. The only thing that will affect it is the value of B, which is 1, for which the index of K is 2. So this will be M212 plus plus. So you can see here, for B being equal to 1, you're always going to increment M212 in this case because it doesn't have any other parents. So it's whenever you see it, that's the count you're going to increase. This would differ obviously if it had parents. It would depend on the parental values. And finally, for 3, C is now 2, and its parents AB are 0, 1. So again, if you refer back, and hopefully I won't make a mistake this time, 3 is for I. J equals 2 means that AB is 0, 1, so J equals 2. And when C equals 2, K is 3, based on our table over here. And so that's plus plus. So I think, using this logic, you can probably figure out what the other ones will be. If you have issues with that, just come to my office hours and we can discuss about that. But that's really, if you keep doing this, you'll end up, you get all your MIJK values and then compute your Bayesian score. Because that's all you need, right? Because all the other terms are either defined or are irrelevant. So yeah, that's essentially what you need to do. I worked through an example by hand, but that's what you'll need to do in your code. So that's like the first big chunk of the video, and it's really the majority of this video. I'll only briefly talk about the other 2 sections. But the second thing that I want to talk about is to do, let me create some gap here. Bayesian score in code. So I won't exactly give you a pseudocode or an algorithm here, but I'll just talk about some of the things that you need to consider. So we worked through this example by hand, but what you need to do programmatically is you need a way to go from a sample of the data set, which is given to you for the 3 different problems, to the count indices. And the key point to note here is you'll want to do this efficiently. Because if you don't do it efficiently, you'll be spending a lot of time looking at your code running while it's searching for different graphs. Because remember, you'll have to compute this Bayesian score many times. So the main point that I want to make here is to think about data structures. That you would use to represent these counts. Again, I won't really give too many hints here because that's the whole point of the project. But, for example, you could have a dictionary. Where, for example, M212, represents accounts, and you have some mapping from sample to string, however you want to encode it, where the string is the key in the dictionary. Dictionaries are fairly powerful. I mean, you could go the quote-unquote naive route of just having a full mapping from sample to key, but that might actually blow up for bigger Bayesian networks, so you'll want to think about how you can extract your key from the sample. The second thing that you could do is have a nested vector. Not sure if that's exactly the right name here, but essentially it would look a little bit like this. This is actually let me use a different color for that. N, so there are n entries in this nested vector, and the entries correspond to I, 1, 2, n, and in each case you would have RIQI. Actually, let me move that over here. RIQI entries. So this might be, these would be more or less depending on however many you had. And so these are the counts essentially. So if this vector is V, then I, so I is the variable, and then you would have some way of incrementing the count for the RIth value. So this would be something like JK essentially. Would correspond to MIJK. That's one thing you could do. If the idea of a nested vector is a little weird, and seems a little difficult to think about, what you can also do is you can have a. So these are just hints. There's no one right way to do this. It's really up to you what design decisions you make. You could have a padded 3D array. Well, a padded 2D or 3D array. So one option would be to have n cross max. So you essentially find the maximum possible RIQI value over all possible i's, and so then you just get a 2D array, but there'll be some padding that you'll need to do depending on how many values. Or this one will probably be a little more space efficient, but because you're computing the max twice, so you have less room for overflow, or you have less amount of overflow. I guess I don't need this. Max I R I. So you find the maximum number of parental instantiations something can have and the maximum number of values it can have, and just construct a 3D, basically a cube. But again, there'll be a lot of padding here as well, because it's only a subset of this that you'll refer to. Which decision you use is up to you. More likely than not, you'll need something for going from parental instantiation, which is a multi-dimensional value, to the index j, right? Because at the end of the day, your parental instantiation, depending on how you implement it, it's a multi-dimensional value of the parents, but you want a single index, the j index. So you should look at, if you're working in Python, look at sub to int. Well, I'm sorry, that's in Julia. I believe it's int to xy, or maybe that's MATLAB. I think that's Python or MATLAB. There's an int to xy function, while in Julia, if it's in 0.6, you can look at sub to int, and if it's in 1.0, you can look at Cartesian, linear indices. But basically this, on Cartesian indices could be useful. Basically what this does is it'll take something like 0, 1, depending on how you've encoded it, and then it'll give it a particular number like 13. And so this is the parental instantiation of something that has 3 parents, and this is the corresponding j. So that's something you'll need to think about. So that's really all the hints I'm going to give in terms of doing this programmatically. Just think carefully about how we did it by hand, and then how you're going to implement that in code. And then the last thing that I'll talk about, even more briefly, is, let me just create some space here. Oops. I guess I have to write something first. Efficient recomputation. Oh, geez. Yeah, you need to get used to this surface. It doesn't stay persistent. So, because remember, you'll have to recompute the Bayesian score many times, or compute the Bayesian score many times, often making a small change to your graph. And it may not be, especially in the third problem where you have 50 variables, it may not be efficient to recompute it from scratch each time. The basic idea is that there's some dynamic programming involved to figure out which subset of MIJK values changes with a small change to the graph. As an example, let's take the example we had before. I mean, of course, it could be a much bigger network than this, but that's something you should think about. Let's say we added this edge here. The only change in terms of the counts would be for I equals 1 when we consider A. Now Qi, instead of being, goes from 1 to 2. And so that's the change that you need to account for. And what I want you to think about in particular, when you introduce an edge, when you're doing your graph, you're doing your neighboring graph search, you're doing K2 search or whatever you're doing, think about nodes that have new parental structures. That's the thing we want you to think about when you're reasoning about what's going to change. That's as much as I'm going to say on this matter, because that's another pivotal part of the assignment, figuring out how to do that efficiently. Note that you can still do it by scratch, but it's just going to take much longer, and probably for your own sake, you want to implement something that can efficiently recompute the score. If this is really becoming challenging, then definitely come see some of us in office hours for some hints on that. So yeah, that's basically what I had. Just to go all the way back to the start to do a quick recap. Ooh, we worked through a lot there. So I talked primarily about the Bayesian score and how to compute it given, or at least how to compute the counts that go into making the Bayesian score given a graph G, some structure G, and a dataset T. I give you some hints about how to do this programmatically, what data structures to think about when thinking about these count indices, and then how to efficiently recompute the score given a small change to the graph. And yeah, I hope this was helpful to some of you, and hopefully it'll help you sail through the programming project. Thanks, guys.